Today, I'm going to be talking about stronger certificates for hypergraph Clique number. I'm Peter, and this is joint work with Venkat Guruswamy at UC Berkeley and Pravesh Kathari at Carnegie Mellon University. So I'd like to start off the talk by discussing certificates for the Clique number for graphs. So suppose we're given a graph G. I'm going to let omega of G be the size of the largest clique of G. And in case you've forgotten what a clique is, it's simply a set S of vertices where every pair of distinct vertices in that set forms an edge in the graph G. And as we know, computing the size of the largest clique in G is NP hard in general. And so instead, we're going to want to certify an upper bound on omega of G when the graph G is instead drawn from the distribution U naught. So we're going to be considering an average case version of this classical NP hard problem. And this distribution U naught will simply be the distribution Gn half, which is a distribution over graphs with n vertices where every possible pair of edge, every possible edge is added with probability half independent. And so a certification algorithm, which is also sometimes called a refutation algorithm, is simply an algorithm A takes as input a graph G and outputs a value omega alg of G that has two properties. The first is correctness, that is omega alg of G is an upper bound on omega of G, the size of the largest clique in G, for any graph G. So that is the algorithm is always upper bounding the true size of the largest clique. And for example, the algorithm A could be outputting, say, something like n, the number of vertices, and that's always an upper bound on the size of the largest clique in G. On the other hand, that's not a very interesting output because it's always trivially the case that that's an upper bound. So we want the second condition to be that the algorithm is doing something useful. That is, the algorithm is with high probability when the graph is drawn from this distribution is getting a value that's at most some omega, where omega is some, say, non-trivial upper bound on the size of the largest clique. And if we have an algorithm A satisfying these two properties, we'll say that A certifies that the largest clique in G is at most omega when the graph G is drawn from this distribution U naught. So the certification question is closely related to the planted clique problem, where here we have this mu naught null distribution, that's Gn half, and we define this planted distribution mu to be a distribution where we sample a graph G by first picking a graph according to this null distribution, and then choosing a random set of size omega and adding every pair of vertices in the set as an edge to the graph G naught, and that becomes the sampled graph G. And so clearly we've planted a clique of size omega in the graph G. And so there's three variants of this planted clique problem. The first is the search variant, where we're given a graph G drawn from this distribution mu, and our goal is to recover S, the planted clique. And as you can see on this picture, there's actually this planted clique highlighted by these red vertices. And so, the search variant, our goal is to recover the set of red vertices. In the distinguishing variant, we simply want to distinguish the two distributions, mu and mu naught, with high probability. And in the certification variant, this is what I've defined on the previous slide, we want to output this value omega alg of G, that is an upper bound on omega G, the size of the largest clique in G. And you can kind of easily see that the certification variant implies the distinguishing variant, so it's stronger. But other than that, reductions between these three variants aren't really known. But it turns out that kind of the best value we can get is omega, that is square root n, so we can recover a clique of size like square root n in the graph G and so on. So even though these variants don't have like formal reductions, they're kind of closely related, and the answer seems to be the same for all of them. And in particular, there's also some evidence of hardness, that is, we have like a sum of squares lower bound for the certification variant at square root n. Okay, so how would we design such a certification or refutation algorithm? Well, there's a pretty simple algorithm, actually. We can let A be the adjacency matrix of the graph G. That is, we let the ijth entry be +1 if this is an edge and -1 if it's not. And then the algorithm is very simple. We output the spectral norm of this matrix. So it turns out that this algorithm actually will satisfy these two properties. So let's just prove it really fast. So to show the first bullet point, we observe that if S is a clique of size omega, then we let X be a vector that's just the 0, 1 indicator of the set S, and then the quadratic form on A will be omega squared. And since X has L2 squared norm, that's omega, this implies the spectral norm of A has to be at least omega. And so that proves that the output of the algorithm was always an upper bound on the on omega of G. And to show the second bullet point, we observe that when G is drawn from Gn half, then this matrix A is a factor random matrix, and so we can upper bound a spectral norm using random matrix theory, and it turns out it's about square root n. So this is a pretty simple spectral refutation algorithm. So in our work, we are just going to consider the same problem, but generalized to hypergraphs. So now we're going to be given a K-uniform hypergraph H, where the hyperedges, in case you've forgotten what a hypergraph is, instead of edges, you have hyperedges, and they're simply subsets of the vertices of size exactly K. So on the right here, I have a hypergraph. It's actually a non-uniform hypergraph because the hyperedges have different sizes, but for our work, we're only going to be considering uniform hypergraphs. And as before, I'm going to let omega h be the size of the largest clique in the hypergraph, which is now a set S of vertices where for every subset of the vertex of the set S of size K, you want this to be a hyperedge. And certification for a fixed K, so we're thinking of K as constant, like say K is 3, is going to be defined similarly. We input a hypergraph H, get an output omega alg of H, and we want omega alg of H to be an upper bound on omega H for any H, and also omega alg of H should be at most omega with high probability when H is drawn from this distribution HK and 1/2, which is a generalization of Gn half, where it's a hypergraph on n vertices, where every hyperedge of set of size exactly K is included in the hypergraph with probability half independent. So that's the problem. It's been studied in 2 previous works, a work of Kodrel-Guang et al. From 2004 and Alan O'Donnell-Wittmer from 2015. And these works use Feige's XOR trick to reduce this problem to CSPs, and they certify a bound where omega is tilde O of n to the 3/4 for any fixed K. And so our theorem improves this. In fact, we show there's a simple spectral algorithm that achieves omega that's square root n. And this essentially matches, our theorem essentially matches the result known for graphs, which is hypergraph where K is 2. So that's our main result. Our algorithm is running in n to the order K time, which is polynomial in the size of the hypergraph. And this log factor hidden in the tilde O is probably not real in the sense that it comes from the fact that we're using some off-the-shelf matrix concentration bounds, which would also yield an extra log factor in the case of graphs. And whereas in the case of graphs, if you do some more complicated bounds on the spectral norm, you can shave this factor off, and we just didn't do that here. Our algorithm is able to handle this distribution HK and P, where P is something that's not a half, but still a constant. And we can even handle a large range of non-constant P as well. We can also get a runtime trade-off where we allow our algorithm to run in larger time, but we certify a better bound on the size of the largest clique. And our algorithm is actually very simple, so I'm just going to describe it in one slide. So let's assume that K is even. We'll let A be a matrix. It's going to be defined similarly as before, and our algorithm is essentially just going to be to compute the spectral norm. So it's going to be a matrix indexed by sets S of size K over 2. And we're going to let the stth entry be, well, it's going to be 0 if S union T has size that's not K. And otherwise, it's +1 if this is a hyperedge, and -1 if it's not. And the way we analyze this matrix is we can write it as the sum over potential hyperedges C of BC times AC, where BC is +1 if C is a hyperedge, -1 if it's not. And AC is a matrix where the stth entry is 0 if S union T is not C, and +1 if S union T is C. And so you can see that A is just the sum of these matrices. And the reason for writing A in this form is that we've now written A as the sum of mean 0 independent random matrices. And so we can apply an off-the-shelf matrix Bernstein concentration to show that this implies the spectral norm of A has to be at most like n to the K over 4. And it's pretty easy to check that the spectral norm of A is always at least omega of H to the K over 2. So this gives us square root n upper bound on omega of H. And that's essentially the proof. And you might be wondering now, well, I assume K is even, and this was kind of crucial because the set S has to have size K over 2. So you might wonder what happens when K is odd. Well, this is actually pretty simple to reduce the odd case to the even case here, where all we do is we just try to guess some vertex I that's in the clique, and then we consider the hypergraph where we take all hyperedges C containing the vertex I, and we just remove I from those hyperedges. So now we get a k-1 uniform hypergraph. And then we can, again, apply the algorithm for the even case here. So that's essentially it for our main theorem. Yeah, thanks for listening to the talk.